In this video, we'll learn about simple harmonic motion. We usually define simple harmonic motion by outlining the conditions that are needed for it to happen. There are two such conditions. The first one is that the magnitude of the force that acts on the object must be proportional to the displacement from a fixed point. The second condition is that the direction of this force is always pointing towards this fixed point. This is a definition that regularly comes up on IB physics exams, mainly on paper 2. In this definition, the fixed point is often called the equilibrium position, and since the magnitude of the force is proportional to the displacement and it points towards the equilibrium position, it follows that the magnitude of the acceleration is also proportional to the displacement, and this direction is towards the equilibrium position. Let's return to the motion of the spring that we started discussing in the previous video. We began with an uncompressed horizontal spring on a table and a small object attached to the spring. We assumed that there are no energy losses during the motion of the spring. Let's compress this spring and observe its motion. When we release the spring, the object will move to the right and the spring will be stretched to its maximum, after which the object moves back towards the left until it reaches its initial position when the spring is fully compressed. This is one complete cycle or oscillation. Let's add the simple scale to our drawing. The center of this scale represents the fixed point or equilibrium position mentioned in the definition. This point is often denoted with 0. Let's say that to the right of the equilibrium position we have the positive direction, and to the left, the negative direction. These directions are assigned arbitrarily. Next, we'll use a table to examine x, the displacement, v, the velocity, f, the force, and a, the acceleration, at the 5 different positions during one oscillation. In the first position, when the spring is fully compressed, the object is as far left of the equilibrium position as possible. This means that the magnitude of its displacement is maximum, and since it is displaced in the negative direction, its displacement is negative. I will denote this with max negative, meaning that the magnitude of the displacement is at its maximum, while the direction or sign of the displacement is negative. If you picture the motion of the object, you will see that at this point it stops for a moment. Because of this, v, velocity, is 0. There are two ways to think about the force that acts on this object. The first is to focus on the spring. As we compress the spring more and more, the force it exerts on the object increases. As a result, at the maximum compression of the spring, the magnitude of the force must be at its maximum. As for the direction of the force, we can imagine that the spring is trying to push the object to the right, in other words, towards the positive direction. This means that the force exerted on the object is pointing to the right, therefore it is positive. So we can conclude that at this position, the magnitude of the force is at its maximum, and it's pointing to the right, so it is positive. The second way to reach this conclusion is by focusing on the definition. The first point in the definition states that the magnitude of the force is proportional to the displacement. Since here the magnitude of the displacement is at its maximum, the magnitude of the force must also be at its maximum. The second point in the definition states that the direction of the force is always towards the fixed point or the equilibrium position. Therefore, the force must be pointing to the right, and since we chose the positive direction to be towards the right, the force here is positive. Moving on to the acceleration, recall that force is equal to mass times acceleration. Since the mass of the object is a scalar and it does not change, the acceleration must behave exactly the same way as the force. Therefore, the magnitude of the acceleration is also at its maximum, and since it is pointing to the right, it is positive. At the second position, the object is passing through the equilibrium position and is moving to the right. At the equilibrium position, displacement is 0. For the velocity, picture the motion of the object from the first, so the most compressed, to the third, so the most stretched position. At the most compressed position, as we said, the object is at rest, so velocity is 0. And as the object moves to the right, it starts to speed up. After the object passes through the equilibrium position, the spring begins to stretch, and as a result, the object starts slowing down. This means that the magnitude of the velocity is at its maximum as the object passes through the equilibrium position. Since the object is moving to the right, so towards the positive direction, velocity is positive. It is relatively straightforward to figure out the force and the acceleration, because both are proportional to the displacement. Since displacement is 0, force and acceleration are also 0. In the third position, the spring is fully stretched. The object is as far to the right as possible, so the magnitude of the displacement is maximum, and its sign is positive. Here, the object again stops for a moment, so velocity is 0. Force is proportional to displacement, so its magnitude is at a maximum, and since it is pointing towards the equilibrium position, so in the negative direction, force here is negative. Acceleration, as usual, behaves the same way as force. In the fourth position, the object is again passing through its equilibrium position, but now it's moving to the left. Logically, displacement is 0, velocity is at its maximum magnitude. However, since the object is moving to the left, so in the negative direction, velocity is negative. Force and acceleration are 0. The final position is exactly the same as the first one, so we get the exact same values for x, v, f, and a. A final concept to mention here is the relationship between the acceleration and the displacement, which we already described in words and said that the magnitude of the acceleration is proportional to the displacement and it points towards the equilibrium position. This is how we write this relationship mathematically. The Greek letter alpha after a means proportional to. So basically, this expression says that acceleration is proportional to negative displacement. Another way to write this is that a, acceleration, is equal to negative k times x, where x is the displacement and k is a constant. What the negative sign in this equation means is that the direction or the sign of the acceleration and the displacement are always opposite. This completes our discussion of the basic concepts about simple harmonic motion.